Edinburgh. We'll be speaking about dualizability and orientability tensor categories.
Okay, thanks. Di mentioned that 25 years ago there was two simultaneous conferences, one on topological field theory, I guess those were early days, and another on subfactors. I thought today, rather than drilling into my own specific work, I might give a bit of developments in the last decade or so that have brought together three sort of very similar cultures. So a lot of us here think about representation theory in the context of tensor categories, Hopf algebras, this kind of thing. In the world of topological field theory, there are sort of two camps. There's a group of people, I would think of Reshetkin, Turayev-Viro, Dijkgraaf-Witten, so constructing some explicit examples of topological field theory, so I'll talk a bit about what I mean by topological field theory. And then there's another group. I would think of people like Baez and Dolan, Jacob Lurie, people following their tradition that think about sort of higher categories, higher or maybe infinity categories. And really what they're really getting at is manifold topology. Okay, and throughout the years there's been a lot of informal interactions between these different groups, but what I want to talk about today is that fairly recently there's enough tools to start proving various folklore results that have been in the air for a long time. So I want to give a sort of overview about some of the key ideas in the interface between these three, and then talk about some recent progress made by many people. So first of all, I'm going to recall very roughly so TFT, this is not the most general definition, but it's the one that we'll use for today. Okay, so let me make a remark about higher categories. I won't make a deal out of it. So if I say a category, I may mean a higher category, and if you're happy with that notion, fine. If not, it's not very important. So a topological field theory valued in some place world of coefficients is, so in particular.
Monodal category, you mean the same as tensor category, or is it different?
No, it's a symmetric. I really mean a symmetric monoidal category. So it's not. It itself is not linear. Maybe it'll be clearer once we go on. So it assigns to closed oriented n-manifolds. So sorry, I should say a TFT, an n-dimensional TFT. So it assigns to closed and oriented n-manifolds some number, some numerical invariant, because we can take it to be in the complex numbers. To closed and oriented n-1 manifolds, it assigns some kind of vector space over C. To closed and oriented n-2 manifolds, it assigns some kind of category, which is a linear category over C. So you might think about like an abelian category of representations of some algebra, something along that line. And then this pattern keeps going all the way down until the very bottom, where we get down to the level of points, and there's only two oriented points. There's the positively and negatively oriented point, and these go to some objects in our category C. So that's the first approximation of the data that a TFT prescribes. Usually we're most interested in things in this top regime, and usually things in the bottom regime are some structure that we use to compute those. Let me say a bit more. I don't want to give a formal introduction to TFTs because I think people are familiar with them in a passing sense at least. But so these constructions, these are functorial for cobordisms, and they satisfy some strong gluing axioms. Okay, so actually I should say, strictly speaking, I should have written a fully extended TFT. If we can go all the way down to a point, this is what's called a fully extended or sometimes fully local TFT. And those are the ones that I'm going to be interested in for today. Okay, so sort of basic orienting result is called the cobordism hypothesis. And it's essentially, so originally due to Baez and Dolan.
Well, just for a little bit of extra help, could you say what happens to one manifold?
No, it depends on what C is. So that's the point. So the kinds of C's that I'll consider in the top dimensions, they all look sort of concrete. And in here they can change. So, but I'll give a bunch of examples of the kinds of C that we care about. They're all going to be actually very familiar. Okay, but it really depends on your choice of C. Okay, so the cobordism hypothesis was first posed by Baez and Dolan, proved essentially by Lurie, but I'm going to put here a third attribution mark of question mark because there are many people that are still working on sort of fleshing out important elements of Lurie's proof, and there are many different groups working on this. So I think it's safe to say that there's not yet the final word on this. It's called a hypothesis because even though it was, you could say it was a conjecture and then a theorem, when it was conjectured, there wasn't enough precise definitions to make a precise conjecture, so it really guided the construction of the right definitions, so it wouldn't quite be fair to call it a conjecture. And that's still to some extent applied to Lurie's proof. He proved it, but there are still some basic mechanisms that needed to be defined to make his proof rigorous. But it's a very important result. So before I say what this is, let me just add a brief extra definition so I can be precise. So I'm also going to need the notion of a framed manifold. So here I was talking about oriented manifolds. So a manifold is framed if we have a trivialization of its tangent bundle. So an N manifold is framed if we can trivialize if we have trivialized its tangent bundle. So this is a much stronger structure than orientation, but I need it in the statement of the cobordism hypothesis. So it has several parts. So it says, first of all, that a framed TFT, so that is an invariant of framed manifolds, is completely determined. Maybe I should say is uniquely determined by the data that you assign to a point. So let me say point in C, and here the point has the trivial framing. So let's not worry about what that means. So this says that there's that all of these higher invariants are completely determined by just a single piece of data that you give in C, and then all the structure that data carries. So that's the first part of the statement. However, so such an object Z of a point must be fully dualizable okay, and I'm going to be spending some time talking about what fully dualizable is. For now, it's a very strong restriction. So it's something like a vector space being finite dimensional. In every case, fully dualizable is a very strong restriction. I'll give a precise definition in a minute. Okay, so that's if you want to start classifying framed TFTs, it says you just have to look inside C and find these finite type objects, and then you're off and running. So moreover, the collection CFD of these fully dualizable objects carries an action, the canonical action of the special orthogonal group in dimension n via reframing of manifolds. Okay, so there's a rich symmetry on these fully dualizable objects, which we can think of as being the partner to a more obvious symmetry of just using the SON action to twist the framing. And then finally, an oriented TFT, so what we started with in the beginning of the discussion, is given by, by providing a trivialization of this action. Okay, so in the talk I want to say what fully dualizable is roughly, and how this SON action looks like in some examples. And the thing I want to emphasize is that at first pass, especially if you read the original sources, this seems like it's all about algebraic topology and homotopy theory and some things that are a bit distant from this workshop. But this recent series of papers, I'm thinking in particular of a paper of Noah Snyder's with Chris Douglas and Chris Schommer-Pries, relate this to things that are of central importance to this workshop. Things like fusion categories, pivotal categories, spherical categories, that sort of thing. Okay, so but before I go on, I want to sort of give a partial answer to Alistair's question about what sort of examples of category C do I have in mind. Okay, so maybe the most familiar example that I have in mind is a two category, which is a sort of basic thing. So it's a two category of algebras and bimodules. So the objects are algebras over the complex numbers. Homs are just bimodules. And then what makes it a two category is that the bimodules themselves have Homs. I should have added here vector spaces. Just the ordinary category of vector spaces is a basic example. So let me start writing those up here. So I'm going to kind of organize the examples by dimension. So sort of in 0 plus 1 dimension, we have just the category of vector spaces, say over C, with the tensor product. I'll explain this numerology as I go. In dimension 1 plus 1, we have this category of algebras. Again, the tensor product is just the tensor product of the underlying vector spaces. Okay, so now on to some So another example, which sort of came up in the last talk, actually, we could look at the collection of finite abelian categories. These are sort of fairly harmless categories to think about. And then, of course, the Homs between such categories are functors. but we want to restrict to what are called right exact functors, so functors that respect short exact sequences on one side. And then the Hams between functors are natural transformations. So these are probably some familiar examples. So that was in sort of dimension 2 plus 0. So in dimension 2 plus 1, we have tensor categories over C. For now, we're going to restrict attention in both of these cases to finite tensor categories. So again, so the objects are tensor categories. It's quite like the first example, except that now our morphisms are bimodule categories. So then those are allowed to have bimodule functors between those, and then those are allowed to further have natural transformations. So once you hear enough of these definitions, it's kind of obvious how to fill it in. One which is maybe less obvious to fill in, which I want to talk about a little bit, is how to organize the collection of braided tensor categories. So I'll read this out, but I'm going to have to explain to you some of these words. So the objects are braided tensor categories, as before. Hams are something called domain walls, which I'll need to explain. And Hams between those are so-called point defects. And then, so these first dimensions are sort of topological. They involve drawing some pictures on the plane. And then after here, this becomes just something about categories. So that's what this numerology means. So here's the sort of dimensionality in the topological sense, and here's the sort of category number increasing on the right. So let me explain a bit about what this collection of braided tensor categories are. So what are domain walls and point defects? So first of all, to do that, to motivate that a bit, I need to say what a braided tensor category is in a way that might be less familiar than the usual definition. So the definition I want to take of a braided tensor category is that this is the same thing. So this is equivalent between what are called locally constant factorization algebras on R2. Okay, and so that's a list of some structures that we can spell out. So first of all, if we have an open subset in R2, then to that we have to assign some object of C. So in this case, we have to assign some category. Okay, if we have a embedding of open sets, only an embedding, not a general map, just an embedding, then it's functorial. So f of u maps directly to f of v. If this is a retract, then this is an equivalence of categories. Okay, and then one other axiom that we have, which is where this factorization comes in, is that if we take the disjoint union of two open sets, we have to give some data identifying this with the tensor product of the corresponding categories. So note here, when I write this square tensor product, it's the same one that came up in the last talk. So it's the Deligne tensor product of categories. Okay, so all of that was just another way of saying braided tensor categories. So let me convince you of that sort of informally. So if we just take a contractible open set, something like that, well, so this is some category, let's call it A. Okay, so if we look at the disjoint union, this has to go to A box A. If we include the disjoint union into a bigger disk, well, this gives us a map. So the bigger disk retracts onto any two disks retract onto one another. They're just retract equivalent. And so this inclusion of two little disks inside of big disk requires us to spell out a map from A tensor A to A. And then another consequence of this retract story is that if we have two different embeddings, so if I look at if I think of this as the first factor and then the second factor, and I switch the order, well, there's a loop in the space of embeddings where I just rotate those around, and that also needs to be assigned some data. And so this gives rise to the braiding. Okay, and I don't want to go into too much detail about the correspondence, but I am claiming that there's a direct correspondence between braided tensor categories and these locally constant factorization algebras, so valued in cat C. So this is kind of a well-known feature. Okay, so the reason that I did that is that the definition of domain walls we're going to take to be locally constant factorization algebras on a stratified space R2 containing one of its coordinate axes. So it's going to be the exact same definitions, except that when I talk about embeddings, when I talk about an embedding of an open set into another, I mean it in the stratified sense. So if this guy has the strata, it has to map to that guy's strata. So for instance, this space, we can draw sort of a picture. Instead of just having R2, we have this line going down the middle. And now let me draw in blue some embeddings. So that's a picture of an embedding of an empty disk, an unstratified disk in, and it's allowed to embed into one of those strata. But if I try to draw this is not, so the blue does not depict a map from the open disk into the whole thing, this guy. Rather, it depicts a map from another stratified disk in. So the definition of embedding of strata is just that you have to respect the strata. It's kind of obvious notion. Okay, and so if we explore what a locally constant factorization algebra in this context would be, you basically see that there are three types of basic open sets. So let me draw the picture again. So there are these pictures that I've already drawn here. Call that A. I could also include an open set over here, and I'm going to give that a different color because I can no longer deform A into B as I could before because there's this boundary that prevents me, and the stratified condition tells me I can't cross. And there's finally one other condition. There's one other type of data I need to give, which is the data on the wall, and that's M. And so basically the data of a domain wall is these three categories. This is a braided tensor category in its own right. This is a braided tensor category in its own right. And now I want to talk to you about what M is. Well, so these same pictures I was drawing before tell us that I have a multiplication map from M tensor M back to M. But this is no longer braided. I don't have the possibility to move these around one another. So this is just a tensor category. Okay. But I have functors. So these pictures, A, M. So this picture tells me that, well, actually even better, let me say this picture that I drew at the start tells me that I have a functor from A to M. It's quite easy to see that it's monoidal, so it's actually a tensor functor from A to M. And it's even not too hard to see that it factors through the braiding. Factors through the Drenfeld center. So amongst the other data that I have to give is a map, not just a tensor functor from A to M, but a tensor functor from A to the center of M. Okay, and we have a similar structure for B, And so part of the data is a tensor map from a tensor braiding opposite to the center of M. And essentially, one checks again that's essentially all of the data that you have to prescribe. So M is a bimodule. It has an action of A and B on either side, but it's even better than a bimodule. It actually has a map to a tensor functor to the Drenfeld center, a braided tensor functor. Okay, great. And so that's the one morphisms. So all of that topology is what informs the one morphisms in this category. And then let me just say kind of briefly that the two morphisms, so Hams from M to N, now you might be able to guess, I draw R2 containing R1 containing a point, and then if I have M, I have N, I have A, and I have B, then now there's only one new type of open set I need to worry about, which is one containing this extra point defect. And so I get a sort of, if I call that X, then X is in particular a bimodule. Okay, and with some compatibilities that I won't spell out now. Okay. So so you can really elaborate the full extent of these structures.
How do you compose one morphism?
So the composition of one morphisms will just be taking the relative tensor product over B. So in pictures, we would draw something like here's A, here's B, and here's C. And we would just sort of take the relative tensor product and then forget that B was in there. Sort of, that's the idea, yeah. And then you also have a vertical composition, which is taking relative tensor product in that direction. Yeah. Okay. All right, so I want to come back to this example. It's the one that's sort of closest to my heart, but I haven't even told you yet what dualizability actually is. I just wanted to get us some grounding into what kinds of categories we're mapping. Okay, so going back to the board, I owe you a definition, sort of what fully dualizable is.
You can just say briefly what the notation 2 plus 2 means? I mean, what?
Yeah, so the numerology here, so first of all, if you add up the two numbers, that's what category number this object is. So this is just the ordinary one category of vector spaces, two category of algebras, and so on. The numerology here is supposed to indicate to you that, let's see, so here you have vector spaces have no multiplications to them at all. So they're zero-dimensional objects from the multiplication point of view. Associative algebras have one multiplication. So that's here. I realized, I'm sorry, I've transposed this. That might be why the confusion. Okay, so categories again have no monoidal structure intrinsic in their definition, but their category number is 2. The category of categories is itself already a 2 category. Okay, so as you go up this ladder, the first number is telling you how many multiplications you have. You have no multiplication structure for vector spaces and categories. You have a single multiplication structure for both algebras and tensor categories, either the multiplication map or the tensor functor. And braided tensor categories, you sort of have 2 compatible multiplications, and that's what gives you the dimensionality. So
EM algebras and
yes. So right. So for the experts, let me write here that this is En algebras in some K category. I'm denoting this as N plus K. But in a more down-to-earth sense, if I'm going to be drawing pictures, I'm always going to be looking at those numbers for what dimension my pictures are. And if I'm going to be doing algebra, I'm always looking at these numbers to say, am I in a category or am I in a 2 category? So all of these take place in a 2 category. As you can see by the Deligne tensor product, it's a structure on the category of categories, whereas these 2 take place in just the category of 1 category of vector spaces.
Did you fix it in R squared because the first number was 2?
Yeah, that's right. Yeah, so that's right. So this is the R2. So this first 2 is that same 2. That's right.
Can you do 3 plus 1?
You can do 3 plus 1, yes, although in practice there's not so many examples of a, well, okay, let's leave it.
Fine, fine.
There's problems with trying to do 3 plus 1. The main one is that there are no examples.
Yes or no question?
You can try to do 3 plus 1 and you find yourself accidentally doing infinity plus 1. That's the best answer I can give. Okay, so let me get on with it. So, so dualizability. Okay, so I'm not going to give a precise definition. I'm going to tell you some definitions that you already know. So it's a hybrid of the notion of rigidity for tensor categories that we already saw in the last talk, and the notion of adjoints of functors. So recall, so x in some tensor category A is rigid if there exists a pair of dual objects and you have some evaluation map and some co-evaluation map and some compatibility. Okay, I think in this audience I can assume that everybody knows what I mean by rigid. And on the other hand, if I'm in if I think about the category of categories, so a functor between 2 categories D and E has a left or right adjoint denoted FR or FL if, okay, so we have some natural transformations, for instance, FR compose F mapped to the identity of D, and the identity of C maps to F compose FR. Okay, and so a basic observation that may well be familiar to you is if you look at these definitions and you cross your eyes, they're really the same data. So here you're assigning, here you have a evaluation and co-evaluation mapping to and from the unit, whereas here the only difference is that you, as Corey mentioned last time, functors can have different endpoints, and so you have a notion of rigidity that takes account of those different endpoints. Okay, so those 2 notions inform the general definition of rigidity, excuse me, of dualizability. But there's a really important point here that helps us a lot when doing concrete computations. So, okay, so if we look at a K-morphism in some n category C, so like in one of those cases, if we look at some level down the ladder, it's dualizable if, let's see, how do I want to say this? If, okay, it is so in the 2 category pi less than or equal to 2 of okay, so I should have named my functor, so or my morphism here. So let's call it F from A to B. It's dualizable if it's so in the 2 category Hom AB. Okay. And the thing I want to stress about this definition is it strips away all of the possible confusions we might have about higher categories, in the sense that whatever a higher category is, if I fix my attention somewhere, then if I look at k morphisms, the HOMs between them are an n minus k category. So the category number drops. And if I have an n minus k category, I can do something called truncation, where I just collapse all the higher stuff. I just throw away anything which is not invertible, and I declare any two morphisms which used to only be isomorphic, I just declare them to be equal. And if I do that, then I get a nice 2 category. And I think most people are familiar with what a 2 category it is. And the notion of dualizability in a 2 category is verbatim the same definition here. It's literally the exact same. You have a map, you want it to have a right or a left adjoint, a right and a left adjoint, and you want to have unit and co-unit axioms. It's the exact same definition. Okay. So that's what it means for a morphism to be dualizable. And then finally, an object of the category, so that's what we need to understand the statement of cobordism hypothesis, is dualizable if, okay, so first of all, it needs to have x star and x double star as in point 1 over here. Okay, so that's the first thing we need. The second thing that we need is that the evaluation and co-evaluation maps that appear in the definition of making this the duals, these need to be one dualizable, which is to say that they themselves need to have evaluation maps and co-evaluation maps. So their evaluation and co-evaluation maps then need to be 2 dualizable. Okay, and so all we're really doing is at every stage we're asking for some kind of finiteness, not on just the raw objects, but on their key, structure morphisms and on the structure morphisms of those structure morphisms and so on. And so if we can get all the way up to dimension k minus 1, then we say that x is k dualizable. As an object, and if we can get all the way to the top, then we say that x is is fully dualizable. Okay. All right. So I want to talk a bit about some examples of dualizability because they start to really hit home for the conference. So first of all, if we look at here, this is automatically, let me write it just in the margin here. This is automatically 0 dualizable, so that's a vacuous statement, but what I'm saying is it's not automatically any more dualizable. But we could ask, if we have a vector space, is it 1 dualizable? That is to say, does it at least have a dual vector space? Okay, and so we can look at what are the 1 dualizable objects. And then we get the finite dimensional vector spaces. So those have a dual, which have an evaluation and a co-evaluation. So the finite dimensional vector spaces are 1 dualizable. Okay, if we look at algebras, well, an algebra, it turns out, is automatically, every object in this category is automatically 1 dualizable. So I'm just going to start writing the numbers here. Okay, so every vector space is 0 dualizable. That's a tautology, but it's non-trivial for it to be 1 dualizable. So here, every algebra, it turns out, is automatically 1 dualizable. So if you like, that's a classical theorem in people like Morita and these people who first defined this category. But if we want it to be 2 dualizable, then we have to look at the finite dimensional semi-simple algebras. Okay, so those are essentially only the matrix rings. Okay, so if we look at the category of categories, we're back to stage 0. There's a general category will have just no such structure. We might wonder, what about one dualizability? I'll talk about that later. But if we want it to be two dualizable, then it needs to be semi-simple as a category and finite. Okay, well, we've already asked for finite here. Okay, so it's a really strong restriction. There can't be any non-trivial extensions. It just has to be a boring bunch of copies of vector spaces to be fully dualizable here. Okay, so coming to tensor categories, they're again automatically one dualizable. And I'm again going to skip what it would mean for them to be two dualizable. And I want to state a sort of very important motivating result here, which is that fusion categories are three dualizable. So this is theorem of Douglas, Schommer-Pries, and Snyder. And this general belief is a sort of folklore for a long time. It's tied up with the Turaya-Viro construction, which makes the same assumption and then essentially defines a three-dimensional TFT. So it's not surprising, but I think what's interesting is that it's very the proof is very explicit, and it really brings these things down to earth. Okay, and if we look at this category of braided tensor categories, so I'm going to again skip the middle dualizability. These are the ones I want to come back to as the part that I'm personally most interested in. So if we look at what are called pre-modular categories, then it's essentially it's a theorem announced but yet unpublished of Fried and Telemann that these are, so they're automatically two dualizable. We'll skip three dualizability, and these are automatically four dualizable. Sorry, not automatically. The theorem is that pre-modular categories are four dualizable. Now this is maybe a bit misleading because I'm not saying that this is a classification of the dualizables. I'm just pointing out that our favorite objects appear as dualizable things on this column.
What is pre-modular?
Say again?
What do you mean by pre-modular?
So pre-modular, so in a modular category you have few axioms. So it's certainly a fusion and a ribbon category. And it has a trivial Muger center. But what I don't ask for is the S and T matrices to be non-degenerate. So if I ask that, then that's what's called modular. So here, I mean pre-modular. You're looking concerned.
Yeah, that's the same as having trivial Muger center.
So sorry. So I want to drop the trivial Muger center. Yeah.
Oh,
So
what's the drop?
yeah. So it's just a ribbon
Symmetric,
fusion
right?
category. Ribbon fusion.
It can be symmetric fusion cases.
Yes, it can be. Yeah, absolutely. Yeah, some basic examples will be symmetric. Yeah, of course. Sorry, that was definitely can have.
And if you don't want oriented, you maybe even want even weaker than that. But anyway.
Yes, yeah. So sorry, I'll talk about orientability and dualizability. That's a good point. Yeah. So sorry, the Fried and Telemann result is I'm a bit paraphrasing it to fit on these lines. So I apologize if I misstate them. Okay, and so I won't go into the proofs of these statements, obviously, but they are. I mean, I think it would be fair to say that a lot of the what you have to do is just unfold these higher category definitions in these examples, and you just really see that they're predicting structures that we cared about already. Okay. So, as in the last talk, I want to push a little bit beyond. So my own interest, the examples that I'm interested in, are not in this finite world. I'm interested in some deformation quantization of some symplectic varieties. And in algebraic geometry, you essentially never have these finite type, fusion type categories. you have to deal with infinite dimensional algebras and categories that are a bit less simple than these. But I want to explain that the way that you move from these small categories that we're more familiar with to these larger categories that you need in algebraic geometry, there's a bunch of analogies that I think are really relevant to this conference between functional analysis, or what I call linear algebra, and these big categories that we need to think about. So I really believe that had I learned functional analysis better as a student, I would have picked some of this up faster. So let me just sketch some of the analogies. So first of all, in linear algebra you have 5-dimensional Hilbert spaces, as we saw last time, and somehow the corresponding thing to those is these finite categories. This finiteness restriction is on the category is just akin to looking at only 5-dimensional Hilbert spaces. Okay, so if you want to move beyond finite dimensions, you need some control, and so you go to the full definition of Hilbert space. It's of course redundant to write complete, but I want to emphasize it. You have some inner product, and you need some completeness with respect to that inner product. Okay, I really want to claim that categories in general are analogous not to vector spaces but to Hilbert spaces, because the basic operations that we have in a Hilbert space, we have addition and addition and subtraction, just basic vector operations, correspond to taking direct sums and quotients in a category. And crucially, the inner product on a Hilbert space, you should think of by analogy as just the Hom pairing, the fact that in a category you have a Hom pairing. So you can turn two objects into a vector space just like you can turn two vectors into a number. Okay, and so the completeness comes in, instead of talking about a Cauchy sequence of vectors in a Hilbert space, we might have some diagram whose colimit we want to consider, and the colimit is defined by how it interacts with the Hom pairing, just like the definition of Cauchy is defined, it can be defined in terms of inner products and absolute convergence. Okay, so then the completeness axiom in a Hilbert space is the same thing as the existence of colimits in categories. Okay, and then a crucial notion is that we now are able to talk about continuous transformations between Hilbert spaces, and it's just an algebraic ability to move limits through the linear map. And in the same way, in categories, you talk about exact or co-continuous functors, and those just have the property that they commute with colimits. Okay. So if you start to look at sort of proofs in this sort of kind of category theory, you really start to recognize that all they're doing is, quite often all that's being done is some direct analog of something that you may be familiar with already in functional analysis. So I hope that's maybe somewhat motivating. So these categories that we construct, the class of categories that you want to study are sometimes called presentable. That's for historical reasons, but their key property is that they have arbitrary colimits. Right. Okay. So I think then I want to start moving towards filling in these gaps. But in order to do that, I also want to start erasing the finites here, here, and here. So I want to recall a theorem of, so this is Brandenburg-Chivrasitu and Johnson-Freyd. So if we look at this full collection of categories without the finiteness condition, and we ask what are the dualizable objects. So in this big world, the dualizable objects have a very natural interpretation. They're categories with enough projectives. So what that means is that every object can be written as a colimit over some diagram of some especially nice objects, and then these guys are what are called compact projective. So that means that if we take Homs against them, this is continuous. Okay, so this is again reflecting something like having a nice basis of vectors and asking that every vector in the Hilbert space can be expressed in some meaningful way that respects the tensor product. Okay, and so I just wanted to say, I'll just say it out loud, that the ideas of the proof are really based on some basic functional analysis. So you have, of course, V always embeds into its dual for any vector space, and likewise, any category, you always have a notion of what you would like its dual category to be. That's what it means to say that it's one dualizable. But just like in functional analysis, you need to start using some topologies because the dual is too big. So you need to look at some space of continuous duals, and they pick out the right notion of continuous duals, and so it's in this way that they're able to prove their theorem.
You just say again, or we can write what the theorem says. What is you just said?
Yeah. So the one dualizable object. So what I'm saying is that the filling in of this first stage here, these are just the, this is their result. Let me say it that way. Okay, and it's a result we recognize. Having enough projectives is a very common assumption to put on a category. It lets you do derived categories and this kind of thing. Okay, so maybe in the last couple minutes I'll talk about some work with Noah and with Adrien Brochier, and I'll just spell out what goes in these two spots, and then if I have a minute, I'll talk about some of the orientability results. So let me just be brief. So this is with Adrien Brochier and Noah Snyder. And Noah, you can tell me if this part of the statement has precedent already. Does it?
No.
Okay. So the claim is that that your tensor category A needs to be rigid in the sense of objects having duals, and it needs to satisfy this dualizability condition of Brandenburg-Chivrasitu and Johnson-Freyd. So these are very natural sort of guesses at what would be dualizable. And here we have to be a bit careful about rigid, because now if we're working with these big categories, as Corey mentioned, you have end objects. So these are like really huge objects. And so I don't want to ask that every object has a dual, because that wouldn't even be true for vector spaces. So the notion of rigid in this big world is that only the compact objects have duals. So that it's generated by compact projective objects, and that the compact objects all have duals. So that's the notion of rigid that one wants. And for braided tensor categories, it turns out that it's the exact same requirement so it should be rigid just as an underlying tensor category. It actually doesn't invoke anything about the braiding. And it also needs to be rigid as an underlying category. Okay, and so Alexei asked about this sort of, you can see a general pattern here of EN algebras and K categories. So a kind of meta question that I would ask is, you know, if you're going to have something dualizable, this is an N plus K category. If you want full dualizability, or maybe you want dualizability up to some level, you're going to find yourself getting to N for free. That's theorems of Lurie, Calaque, and Scheimbauer. They tell you that you get to N for free. If you want to move past, you're going to have to ask for some dualizability as an underlying object. And then you're going to have some compatibility, such as rigidity here. And I think it should be an interesting program. There are some ideas already in some of Lurie's papers to vary n and work out what is the exact notion of rigidity that one wants. Okay, and let me just finish by saying a bit about some of the results about orientability. This will just take me a minute. So I'm going to have to abbreviate a bit. But so for tensor categories, okay, so if you're rigid, and I'm going to suppress the BCJF condition, if you're rigid, then there's another structure that you can ask for a rigid category to have, which is pivotal. Okay, so this was 2 dualizable, and the 2 dualizable guys carry an action of SO2, and it essentially already follows from the story in the finite situation that Noah and the Chris's proved that to be fixed, so to be SO2 fixed is to be pivotal, or rather, at least if you are pivotal, then you are SO2 fixed. It's quite interesting. They find a weakening, a sort of Merida theory type weakening of the notion of pivotal, which I think could be explored more. But certainly pivotal is enough to exhibit SO2 fixed. If you're fusion, then you're 3 dualizable. That was their result that I mentioned. And then you can ask, when are you SO3 fixed? And they give another nice answer. They say, well, if you you can trivialize the SO3 action by first trivializing the SO2 action. And if you do that, then if you want to move from a pivotal structure fixing your SO2 action to a structure fixing your SO3 action, then this is the notion of spherical. Okay, and so then finally let me close by saying what our work in progress with Noah and Adrien is gunning towards. So if you're so to be SO2 fixed, so this is already kind of known. This is to be what's called balanced. So this is a version of having a ribbon element, but it's not. It's ribbon without being dualizable. So this is in the case of 2 dualizable. And if you're 3 dualizable, that means that you're rigid. And then there's a natural condition that you might guess for SO3 fixed, and that is indeed the case. You need to be ribbon. So the ribbon condition is a further compatibility between the dualizable, the rigidity, and the balancing. It's called ribbon. So it's probably familiar to many people here. And then if you go to 4 dimensions, then that's when you start to get into the reign of Freyd and Telemann. So I think maybe I'll just say briefly, these computations proceed by a explicit decomposition, not quite of SO3 as a homotopy type, but of what's called BSO3, its classifying space. And so in their earlier work, Noah and the Chris's had made this abstract space very concrete. They gave you an explicit cell decomposition. They said you start with a point, you add a 2 cell, you glue on a 3 cell, and then so they give you an explicit algorithmic way to construct this thing, and then analyzing those maps give you these sorts of results. Okay, thank you.
Any more questions for David?
Can you say again your generalized notion of this rigid? So it's kind of generated by, it's like, can you tell me what rigid means again in the more generalized?
Well, okay, so in order to be 3 dualizable, first of all, it's easy to see that you need to be 1 dualizable. So it means a category has to be generated by its compact projectives under colimits. And then the right notion of rigid for this is to ask that the compact objects are rigid. So that means that if you have a compact object, then it has a left dual and a right dual. It doesn't then imply that all objects do, because there's some non-commutativity of taking colimits.
But rigid objects are automatically compact projected, right, from the adjointness of the tensor functor. Is that objects that have
You can be compact but not compact projective and have.
Yeah.
Oh, okay.
Just take your favorite finite tensor category that's not semi-simple,
Okay, yeah.
and then sort of complete
Yeah.
it.
Yeah. So that's a sort of no-go thing, that if the unit already is compact projective, and all compact projectives are dualizable, then you force yourself to be semi-simple. So there's a delicate balance you have to make, and so you only ask that the compacts be dualizable.
Am I right in thinking that to be n-dualizable, to have that top level, that's where that finiteness is coming in? Like you.
Yeah, that's right. That's a good observation. I meant to stress that more. You can see that you always would need a really strong finiteness at the top level, because you have to get numbers out, and you're computing the dimensions of some spaces, and they have to be finite, and that essentially always tells you that you're going to have at the top level it's going to tell you that always, if you're going to be fully dualizable, already at level n-2, you have to have some kind of small category, if you're in this restrictive Morita sort of world. That's right. So that was actually one of our motivations, is that there's all this nice story about modular categories and fusion categories, but actually in this framework, a lot of results will generalize, but just not to the very top level. Other results like classification of representations, construction of algebra objects and stuff, it goes through in this larger setting.
I hear you're saying like for like ribbon fusion type of things, these pre-modular things, you would get some kind of TFT, but not like all the way to the.
Yeah, so you would get you would get there a different use of the terminology, what sometimes people call a 3+1 dimensional TFT, which is it wants to be a 4-dimensional TFT, has all the features that a 4-dimensional TFT would have, except for you can't actually evaluate it on 4 manifolds. You can only evaluate it on 3 manifolds and below, but when you do that, it will have all the structure as if the 4 thing made sense. Yeah.
Any other questions? Yeah, let's thank David again.
It's tea time now, but